Hello! It's getting to that part of the semester where we're reviewing for finals. So I thought this week I would do a review of force problems. So there are many force problems, but all of them share something in common. They all use the same general process to solve them. In this video, we're going to learn the process and we're going to use it to solve this problem. A 3.87 kilogram box rests on a slope with an angle of 23 degrees. What is the minimum coefficient of static friction that would prevent the box from sliding? So every force problem follows the same general procedure. If you follow this procedure, you'll be able to solve force problems no matter what forces there are, be they tension, be they weight, spring force, you name it. So what is this process? Well, the first step is to identify the object of interest. This is the object that is important. It's what the problem is about. The second step, identify the forces on the object and its acceleration and draw the free body diagram. Step 3, fill out Newton's second law with the x components and y components of each of the forces. Step 4, solve the equation algebraically, eliminating unwanted variables and isolating the desired variable. Step 5, calculate the answer. Now it's important to do step 5 last because where many students trip up is that they want to jump right to the calculation, and so they end up memorizing the final form of the equations for specific problems rather than learning the general process they can apply to any problem. So we'll just put those over to the left and have them to view as we solve our problem. All right, we got the problem here again, our box on a slope. First thing we want to do is to write down the information the box gives us. So to identify the variables that we have, we know the mass is equal to 3.87 kilograms. We know the angle is equal to 23 degrees. And of course, we know the constant g, the strength of gravity, is 9.8 meters per second squared. Okay, so I've drawn a picture. The next step is to identify the object of interest. Now there's two possible objects it could be. It could be the box, or it could be the slope. And in this case, what's moving, or what could move? The box is what could be moving. So the box is our object of interest. Second step is to identify the forces on the object. And I know it's covered by the whatever it is over there, the interface. Let's just fix that real quick. Identify the forces on the object. Now, on the Earth's surface, every object has a weight that points downward. That's our first force, weight. Now, why doesn't the box just fall straight to the center of the Earth? That's because there's a ramp in the way. And when a surface is in the way of an object, it exerts a normal force. Normal meaning the direction perpendicular to the surface. So the normal force in this case points at an angle this way. But also we know that the box is not moving. See, static friction prevents the box from sliding. So we can tell which way static friction is going to point. It has to be either up the slope or down the slope because it points parallel to the surface. And it has to balance the free body diagram so that all the forces add up to 0. So the static friction is going to point in this direction. Now we're not quite done here yet because we need some angles and we need the acceleration. Acceleration is easy. A equals 0. And let's not forget to label this force of static friction. So how do we handle the angles? Well, remember, when we write a coordinate system, it can be at any orientation as long as the two axes are 90 degrees from each other. So what we can do with the slope is draw the y-axis perpendicular to the surface and the x-axis parallel to the surface. Why do we do this instead of having it horizontal and vertical? The reason is because this way, more of the vectors lie on the axes. So we have to break fewer of them into components. So the last thing is the angle. Where do you think this angle of the slope would be on our free body diagram? Well, some of you might think it's this angle. because that is with respect to the horizontal. But if you look at it, those don't look the same. This one's wider, this one's sharper. So where the angle actually goes is right here. It's with respect to the y-axis. And there we go. We have our complete free body diagram. The next step is we want to fill out Newton's second law with the x and y components of the forces. So Newton's second law is the sum of the forces, it's a vector equation, is equal to the object's mass times its acceleration. In this case, our object is not accelerating, which means the acceleration is 0. So in this case, the sum of the forces equals 0. This is a two-dimensional problem, which means we need to write this equation twice, once with x components and once with y components. So in the x dimension, we have static friction minus weight x equals 0. Right? Because weight x points in the diagonal direction, which means it has a component that is parallel to the x-axis. We fill out this triangle. I can't do it because it wants me to attach the theta. We fill out this triangle. No, don't attach the theta. Dang it. Pretend this is a right triangle. Pretend that's a right triangle. This green line is the x component of weight, and it's parallel to the x-axis. In the y dimension, we have two forces still. We have normal force minus the y component of weight equals 0. And of course, we can rearrange these to get static friction is equal to the x component of weight, and normal force is equal to the y component of weight. Now it's important to notice this here. Some of you might have memorized that normal force is equal to weight. That is in fact not true. It is sometimes true for particular problems, but in general, it is not true. And how do you know the difference? The difference is when you write Newton's second law, if the normal force ends up being equal to the weight or not. In this case, the normal force is not equal to the weight, it's only equal to the y component of the weight. All right, zooming in on this triangle, we want to find the components. So we've got the x component, the y component, and the magnitude forming a right triangle together. So the way that we find the x and y components is x is the opposite side of the triangle. It's important to note that this is the y-axis, and this is the x-axis. The x component is the opposite side of the triangle. So wx is equal to w times the sine of the angle. Now you're thinking, wait a minute, I learned x component as cosine. Why is it sine? The reason is because in this case, the angle is with respect to the y-axis, not the x-axis. And when the angle is with respect to the y-axis, the sine and cosine get flipped. The x component is now the sine of the angle, and the y component is now the cosine. Wait, y equals weight times cosine theta. Okay, now these w's aren't really that useful, so let's find an expression that makes more sense to us. Weight is equal to mass times g. So weight x equals mg sine theta. Weight y equals mg cos theta. We've also got this variable frictional force, but the problem is asking us to find the coefficient of static friction, specifically the minimum coefficient of static friction. So we need a relation to replace static friction force as well. Luckily, when we have the maximum static friction, it is equal to the coefficient of static friction times the normal force, which means static friction can be anything up to the coefficient of static friction times the normal force. It can also be less, which is why, since the problem asks for the minimum coefficient of static friction, we can use this equation. So now that we have our three expressions, we can plug those in to our two equations right here. That gives us coefficient of static friction times normal force is equal to mass times g times sine angle, and normal force is equal to mass times g times cosine angle. Notice again that it is not equal to mg, it is mg cosine theta. Just label these, this is the x equation and this is the y equation. That is not going to be important anymore, but it does remind us where these equations came from. Okay, now we have an equation with the variable we're looking for. This one. We're looking for the static friction. However, we also have a variable that we don't know, the normal force. So we have to look to the y equation to substitute in for the normal force. Coefficient of static friction times mg cos theta is equal to mg sine theta. Now you might be wondering why I went this long without plugging in numbers. After all, we've been able to put numbers into these variables for a long time. We could have simplified them by doing some calculations ahead of time, right? Well, here's the reason why you want to save that for later. If you look at both sides, they both have an m and a g, which means if we divide both sides by mg, it cancels out completely. And we're left with static friction coefficient is equal to the sine of the angle divided by the cosine of the angle, which can be simplified to the tangent of the angle. And our angle is 23 degrees, and the tangent of 23 degrees is 0.42. So notice here, the minimum coefficient of static friction required to prevent an object from moving on a slope does not depend on the object's mass at all. In fact, it doesn't depend on the gravity either. It only depends on the angle of the slope. So that's it for today. We practiced a problem finding the minimum coefficient of static friction that would be required to prevent a box from sliding down the slope. We did it by following the 5-step process of force problems: identifying the object of interest, identifying the forces on the object, the acceleration, and drawing the free body diagram, filling out Newton's second law twice, once with the x components of the forces and once with the y components of the forces, solving the equations algebraically to eliminate unwanted variables and isolate the desired variable, and finally, calculating the answer. Using this method, you can solve not only box on a slope problems, but any problems involving forces and accelerations. Thanks for watching. I hope this review was helpful for you as you study for finals. If you would like personalized tutoring, you can visit my website, physicstutorchris.com. And if you don't need tutoring, but you'd like to support my business, you can visit my Patreon page. You can also like the video and subscribe, and share it with any of your friends you think might benefit from it. Thanks again for watching. Happy studying.